So I got a question for class that I think is probably we can suspend our further work just for a second while I deal with this. Let me give you an example. And this is where the split x fifth minus 1 over here. So the specific question that was directed at me was, and hopefully this will illustrate, is if you have a Galois extension, you have these automorphisms, right? Now, if you have an irreducible polynomial over the base field, and that polynomial splits in the Galois extension, and you know that every automorphism of F takes a root of that polynomial to another root of that polynomial. And also it has to be transitive in the following sense. If you have two roots of said irreducible polynomial, u and v, there has to be some automorphism that takes u to v. Now, if this polynomial has n roots, then it turns out that it has to be a transitive subgroup plus n, right? But it can't be just any. So let's look at this example here. And we kind of look at its Galois group and the automorphisms. By the way, anybody want to guess the Galois group? No, maybe we can figure this out. Right. Now, don't need a splitting field to get this root, right? We've already got one. So this is the splitting field. So improved version. X4. Right? But this form is actually convenient because certainly one is a root. Can anybody tell me what the other roots are? So the roots x cubed, what's x squared, what's x plus 1 are roots x to the 5 minus 1 that are not 1. Right. So it's the other ones, right? So how do we do this? Well, this one's actually a little bit more convenient. Although this polynomial is factorable, it's a little bit more tricky. And actually, to factor that polynomial, it helps to know the roots in the first place. So it occurs to me that maybe not everybody, how many of you have ever been exposed to any complex? It doesn't even have to be fancy complex analysis, but of course in complex variables. Yeah, well, this is probably not going to hurt for review then. So how do we solve this? Right. In fact, sometimes if you get a really good trigonometry course and they've got time, they might do this. So think of this. This, of course, has one real root and two pairs of complex conjugates. And you can think of this on the unit circle. Another way to write one is that, right? Everybody know that old chestnut, that's cosine 2 pi plus I sine 2 pi. But not just this. Actually, 2 pi I k for any k and z works as well. Agreed? And this actually helps me get my solutions because my x is e 2 pi k I with 5. And let's see what happens with this. I get e to the 2 pi I over 5, e to the 4 pi I over 5, e to the 6 pi I over 5, e to the 8 pi I over 5, and e to the 10 pi I over 5, which is actually 1, which is not one of my fun ones. And then it cycles back, right? And these roots actually appear at 72 degrees. And actually, this is if you want to construct from ruler and straight edge, ruler and compass, the perfect pentagon. These roots show up. This is e to the 2 pi I 5, e to the 4 pi I 5, and 8 pi I over 5. Right now, because I'm a lazy man, I'm going to call this. Everybody okay so far? Okay, so what does the splitting field of this polynomial look like? Well, F is the smallest field that contains Q and these roots. Right? Now I did write some silliness in there. I put in all the roots of x to the 5 minus 1. And of course the 1 is ridiculous. It's already Q, right? I kind of wasted all our time here. And not only that, what else is a waste of my time? Conjugate pairs are actually, it turns out, a waste of time, but it goes even farther than that, because notice if you have omega, that's all you need, baby, right? Because once you have omega in the field, then you've got omega squared, omega cubed, omega 4. And actually, because 5 is prime, it really doesn't matter. In fact, instead of adjoining omega, I could have adjoined omega squared, right? What are the powers of omega squared? Omega squared, omega 4, omega 6, which is omega, right? And so now I've got omega again, right? So actually it turns out that I'll just stick on omega because it's convenient, but any of them will do except for 1. So what is the degree of the extension? Now, let me first note that x to the 5 is not irreducible. Is everybody buying that? This is, by the way, maybe I should go through this. This is actually, let me give you a proof. One proof is you can actually use this diagram here. And since the roots come in conjugate pairs, notice that these are conjugate pairs and these are conjugate pairs. And you can use that for leverage and actually figure out how to factor that polynomial, right? But I'm going to show you a trick that's quite worth looking at. So if I look at this right here, this is equal to equals y4 plus 5y squared 5y cubed plus 10y squared plus 10y plus 5. So this is 5 Eisenstein. This polynomial is irreducible, and this is just a transformation by a constant. It's easy to argue that if this polynomial reduces, then do the translation, and this polynomial will reduce as well. So this thing actually is irreducible. So what does that give me? Well, let me collect some thoughts at this juncture. X to the 4 plus x cubed plus x squared plus x plus 1 is irreducible. Degree 4 over the cube. Its roots are omega squared, omega cubed, omega 4. In keeping with my notation here. So the Galois group of F over the cube is isomorphic to a transitive subgroup of S4. And I gave you a list of these a time or two ago, perhaps, but I'll list them again. So lists are S4, A4, equal on square, cyclic of order 4, and Z2 sum Z2, and a specific one. There are other Z2s inside of S4, but that's the one that's transitive because this allows you to permute all the roots. Now, this one actually, anybody want to guess what it is? It's one of those in those lists. Well, actually, I'm going to do this really from the point of view of automorphisms, right? So note that the degree of F over Q is the degree of Q omega. This is from this earlier observation that the splitting field F is just really Q omega. And what's the degree of this? It's 4, right? Because omega is a root of an irreducible 4th degree polynomial Q. So, okay, I feel like one of those detectives smoking cigarettes in one of those noir films, right? I'm kind of paring down my list of suspects here. 3 of these groups are now off the charts, right? If the Galois, if the extensions of degree 4 and it's Galois because it's splitting field of this, those Galois groups all too big, right? The degree of this extension should be equal to the order of the Galois group. So here are your choices: C4 and Z2, Z2. That's it. Let's see if we can figure out what happens. So, what are the automorphisms? Of Q omega over Q. Automorphisms that basis. Well, guess what? Q omega this is the set of things that look like Q0 plus Q1 omega plus Q2 omega squared plus Q3 omega cubed. Any automorphism. So the automorphisms all have to fix every rational number. And any automorphism is completely determined by what happens to omega. Right? So and here I'm sort of helped out by the fact that I know that the group has to be transitive. So my roots of that polynomial are the powers of omega. So I know that here are my possibilities. Omega goes to omega. I could do that. But if omega goes to omega, then any power of omega goes to that same power of omega. And there we go. This is the identity. Number two, omega could go to omega squared. Agree? Now, let's also remember that, of course, omega to the fifth power is equal to 1, right? That's going to help me. We could have omega go to omega squared, right? And I know that that's a possibility. And the reason I know that is because omega is a root of that polynomial, so is omega squared. So by transitivity, I know that given any two roots, there has to be an automorphism that takes omega to omega squared. And now what we got to do is just sit back, have a hot dog, and see what happens to everything else. So omega squared, if omega goes to omega squared, then omega squared must go to omega 4. Right? And so omega cubed could go to omega 6, which is omega. And omega 4, which is, of course, the inverse of this, must go to omega cubed. Yes.
So to show that that's an automorphism, you're just saying that. So it might be a possibility since it permutes roots.
It has to be a possibility.
And then it has to be because
Omega and omega squared are two roots of that. So there has to be an automorphism that takes omega to omega squared.
So permuting roots is a necessary condition, but taking one root to another, like you always have one.
You always have one. If you have any pair of roots, there's always an automorphism that takes one to the other. Right. But if you have like a collection of roots, there's no guarantee that you can do whatever you want. And when we exhaust this, I'll give you an example. Notice that my selection of omega going to omega squared determined everything else. I know that omega must go to another root, and I know that given any pair of roots, there is an automorphism that takes here, and that tells you everything else that has to happen. Well, just following that lead, I could have omega goes to omega cubed. Right, do that. So where does omega squared go? It goes to omega 6, which is omega. Where does omega cubed go? It should go to omega 4. And where does omega 4 go? It should go to omega. Notice these again are permutations of the root. And I wish I thought my columns out better, but your last possibility is omega goes to omega 4. By the way, anybody want to guess what this automorphism is? It's complex conjugation, right? Oh, and we should see that in action. Omega squared goes to omega 4 squared, which is omega 8, omega cubed. So it goes to its conjugate. Omega cubed goes to omega 7, which is omega squared. And omega 4. So if I think about this as permutations, another way to write this is This is the permutation E. This is the permutation. 1 goes to 2, 2 goes to 4, 4 goes to 3, and 3 better go to 1. Does. This is the permutation 1, 3, 4, 2, better go to 1. And this is the permutation 1, 4, 2, 3. Notice the square of this is this. The square of this is also this. This is actually isomorphic to Z4. Or I think I might call it C4, cyclic 4. Notice this permutation. You have to compose this automorphism 4 times to get the identity. So notice that every one of these gave a permutation of the roots. Right. But it was certainly far from being everything in it's far from being everything in S4, right? So for example, you cannot do or even for this particular case right. So you can't just go in there and say, okay, I'm going to take omega to omega squared to omega cubed, and then omega cubed back here. You can't do it because the structure of the roots here forces you. Once you make a choice on omega, everything else is set in stone. Your question? So different situations for different polynomials that come up, and there's lots of things that can come up. Like as I pointed out, I gave you all a list of up to isomorphism transitive subgroups of Sn for n equals all the way up to n equals 5, and I stopped there because the number of isomorphism classes of transitive subgroups of S6, there's like 16 of them. Right, and it gets out of hand pretty quickly. Okay, does that clear things up a little bit? Is that example color? Okay, so let's kind of see what we were here. Okay, so let's pick up again on the splitting fields, and we'll get the separability here. Okay, so here's a theorem that you all I need to express to you, and I mentioned last time that this gets into semi-heavy duty set theory. You have to distinguish between sets and classes and all this. There's some Zorn's limit going on. I'm kind of going to skip over this. If you're interested, though, we can go over it ourselves. Every field K has an algebraic closure. And let me clarify for sure what I mean by that. K contains K bar is a field such that every polynomial over K splits in K bar. So an algebraic closure, what we talked about last time is what it meant to be algebraically closed. Basically, so here's this is extremely fast and loose. But how do you get to the algebraic closure? Just take the splitting field of all polynomials with coefficients in K, just all of them. And that's where you need the Zorn's limit and the set theory stuff, because what you do is you kind of build towers of fields and show them satisfy Zorn's limit and so forth. And any two algebraic closures of K are K isomorphic. So sometimes if I'm sloppy, I might say the algebraic closure, even though that's probably a little bit sloppy. But any two algebraic closures are isomorphic as fields that fix K. Theorem, and this will be my kind of mark on that. Let K be a field, and we'll say S, a set of polynomials. Polynomials in Kx. Then there exists a splitting field for S over K. And actually, I probably sloppy Jim. I probably really should have put this theorem before the other one, but that's fine. Let me point out that we already know this result if the set of polynomials is a finite set, right? So say you've got 100,000 polynomials. Why is it okay to be a finite set? Well, the splitting set of 100,000 polynomials is, or the splitting field of a set of 100,000 polynomials. You take all the roots of those polynomials, throw them into the field, right? You can make that the splitting field of a single polynomial just by taking all 100,000 polynomials and multiplying them together into a big fat polynomial. It's got the same collection of roots. And so we've already done this for any finite set. You know, we actually explicitly did this. But this is, if the set is infinite, then you can find theorem 8.3.5 as a special case of this, where the special case would be take S to be the set of all polynomials with coefficients in K. Okay. Any questions? Okay, so we talked about normality. And there's another kind of companion thing that we need. It's a little bit more subtle, I've always thought. Separability. And let me say that, of course, you can always have multiple roots of polynomials, but this is really, separability is only something that you have to really worry about in characteristic P. P is non-zero prime. It turns out that if you have an irreducible polynomial in characteristic 0, it's always separable. That is to say, irreducible polynomials in characteristic 0 cannot have multiple roots, right? So let me start to make this more precise. Definition. Let's let K and F be, let K be a field and X and KX irreducible. Then F is separable. If F factors into distinct That's the operative word, distinct linear factors. In some field extension. Or splitting field, in some fields, or X. Okay. So what it means for a polynomial to be separable is when you go to its splitting field. So we know that we can go to a field that's big enough to where it splits into linear factors. All the linear factors are different. An element well, let me say an algebraic element. U and F, some field extension containing K is separable. By the way, you might want to guess. So we know a polynomial separable splits into irreducible. Let me say an irreducible polynomial separable if in a splitting field splits into linear factors. What do you suppose it means for an element to be separable? Okay, there we go. So take its minimal. So given a U, if it's algebraic, I can find like a unique minimal polynomial. If its minimal polynomial over K is separable. So take your, you want to talk about separable element, take your element, look at its minimum polynomial. If that's a separable polynomial, then we say that the element U is, if K is in F and every element of F is separable over K, we say F is separable. Let me make a quick observation that if you have a field extension, if you say that every element is separable over K, you're implicitly saying that every element is algebraic, right? So separable extensions are algebraic. And if every element of your extension is separable, then we say that F is a separable extension. Okay, so far so good. We can get an example or two. And F goes algebraic over K, then F. So in characteristic 0, it turns out that any algebraic extension is separable. We're going to see a theorem to that regard here, but obviously anything you can think of, you get distinct roots for your polynomials. Let me give you a non-example, and this one will probably be familiar to some of you because I think almost everybody kind of dug this example out when I asked for extensions for Galois. Oh, let me give you another example. If K and F are finite, then F is separable over K. Okay, that's another one that I haven't proved yet. Both of these statements I've made as an example. You might kind of muck around with it and sort of see what happens, but both of these statements will be proven down the road. If you have an extension of finite fields, always separate. So then scratch your coconut a little bit and say, okay, is there an algebraic extension that's not separate? Well, again, round up the usual suspects. Can't be characteristic zero, can't be finite. So it would have to be an extension of infinite fields characteristic P. So this example, and of course, some of those can possibly be separable as well, but here's a non-example. These are both infinite fields. The first one is rational, the bottom one is rational functions in the variable x squared, and the top one is rational functions in the variable f. The fact that this is a 2 and that is a 2 is actually significant. That makes my example. This is an algebraic extension. And in fact, the degree is 2. In fact, I'll go one step further for you. Of course, these are rational functions, so they can be quotients of polynomials. But let me point out that if you have any polynomial in the variable x, over the field of 2 elements, if you square that thing, by the freshman's dream, this is now, there aren't any middle cross terms. All the powers of x are now even. Now, that's just a polynomial, but it's easy to see that if you have a quotient of 2 polynomials and you square it, you get the same effect. So in particular, if you have anything here and you square it, you end up down here. So this extension actually is a degree 2, and a basis of this over this would be just 1 in x. Right? So in particular, x is algebraic. X is a root of the polynomial t squared notice monic polynomial, in fact, and that root x squared is in f2x squared. Right? X is a root of this. In the splitting field, so the root x is a double root. This polynomial here is irreducible. It has to be, because this is a degree 2 polynomial, right? And so it has at most 2 roots. If it's got 1 root downstairs, then it's got to have both roots downstairs. And 1 root is x, and that's not downstairs. So this actually has to be an irreducible polynomial, and that's how it factors. Yes.
Is that supposed to have a bracket t and f2 of x squared?
Oh, yeah. I should have said over, but let's do that. Absolutely. So here, this is an example of an element and a polynomial that are not separable, because it's minimal polynomial. And I know it's minimal because you can't do better than 2 unless you're downstairs. It's minimal polynomial is degree 2 and has a double root. Okay, any questions on that? let me give you a lemma here, kind of a fun little lemma that will help us with one of my crazy claims. My examples. Lemma. Let K suppose these are fields. The element U and F with minimal polynomial f of x and kx is separable over k. If and only if GCD f of x f prime of x is equal to 1. Okay. So what this is really a statement about. I try to get away with several things, right? So the element F is separable if and only if, by definition, its minimal polynomial is separable. And this happens if and only if the GCD of F and F prime is 1. Okay, so so anybody, any ideas why this might be true?
I think like if the if f of x and f prime of x will have like a common root, that will be
Okay.
double root in the original.
Suppose F prime is not equal to 1. So what do we know about this? So you get the greatest common divisor of f and f prime is not 1. Okay, so let we will say that degree d of x must be at least 1. So now what do we know about the greatest common divisor in this situation? One of my favorite things. Yeah. So d of x equals a of x f of x plus b of x prime of x for a of x, b of x, and a of x. Okay. So where do we take it from here? We also know that well, there's linear combination. We also know d of x divides both f of x and f prime of x, because after all, it is divides. Agree? So this means any root of d of x is a root of both f of x and f prime of x. Everybody okay with me? So, see if I see kind of a problem with that. So let's see. D of x. Then x minus z. Well, then in a splitting field for f of x, right? Because if z is root of d of x, it has to be a root of f of x, and that appears to some power, right? So f prime of x, if you feel like you're doing calculus here, is x minus k, or I'm sorry, x minus z, the k power in prime of x, plus k x minus z, k minus 1 d of x. Oh, and here we'll say that d of x has no factor of x minus z. Right, that is to say, we've sucked all possible powers of x minus z out of that, and g of x is relatively prime to it. Right? Everybody agree with me? Now, notice that f prime of z is equal to 0 because it's got a double root here, which is z minus z to the k d prime of z plus k times C minus E, K minus one, G of Z. Right? Now notice that K is at least one, so this bit is zero, right? And notice that this is also, notice that if K is bigger than one, then, or I'm sorry. If K equals one, then this is just G of Z, and G of Z is not zero because we pulled all the factors out. So K must be bigger than one for this condition of the root being a root of both F and F prime. Therefore, F is not separable. So that establishes the forward direction that if the minimal polynomial is separable, then the GCD of F and F prime is one. Because it's not one, then you get not separable. Any questions on that? We'll go the backwards direction next. Questions? All right. Well, we will see you all on Friday.